Hello students, this is Dr. Aisha Nazuk and welcome back to my channel. This is my second video in the playlist for probability theory. In the first video I introduced you with the basic concepts of probability. Today we are going to cover the topic of rules of counting, which includes the concepts of factorial, combination, permutation and some other things. Without further waiting, let's start today's lecture. Okay, suppose we want to count the number of ways two independent events can be performed. How can we do that? First of all, you need to refresh the concept of independent events. If the occurrence of one event does not impact the occurrence of the other event, that means that the two events are independent. Let's say if event A can occur in n1 ways, n1 could be any number, right? Event A can occur in n1 ways while event B can occur in another n2 ways. Both n1 and n2 are some numbers. Then the number of ways these events can occur together is equal to n1 multiplied by n2. So let's further clarify this rule with the help of one applied example. Suppose we want to dress up and we have 10 choices for tuxedo shirts or the formal shirts. We have 15 dress pants and 7 neckties. So in how many different ways can I dress up? Like in my wardrobe, I have 10 formal shirts, 15 dress pants and 7 neckties. So basically these are three events. Event A, which is selection of a shirt, could be performed in 10 different ways. Event B, which is selection of a dress pant, it could again be performed in 15 different ways. And selection of a necktie could be performed in 7 different ways. Note that here I am assuming that we are not sensitive about combination of a particular shirt with a particular pant or a necktie. So we are assuming that any shirt could go with any dress pant or any necktie. Let's say this is the hypothesis. In this scenario, selection of a shirt is independent of a selection of a pant, which is in turn independent of the selection of a necktie. So I can dress up in 10 into 15 into 7, which is a pretty big number. So if there are no assumption, I have a pretty, you could say, large number of ways in which I can dress up. So by using these 10 shirts, 15 dress pants and 7 neckties, there are 1050 different ways I can dress up. Okay. Of course, you might be thinking that in general or in practice it's not the case. People do have a sense of, choosing which particular shirt color will go with a particular dress pant color. So as you learn more concepts of rules of counting and imposing some restrictions, you will learn how to count number of ways if there are some restrictions, extra restriction imposed on the data. For now, in this example, there are no restrictions. Okay, next we introduce this factorial operator, which is represented by the symbol n factorial. So if n is any number, its factorial is calculated by keep on deflating it by 1 unit and then keep on multiplying the consecutive terms until you reach 1. For example, if you have to calculate 6 factorial, it is equal to 6 into 5 into 4 into 3 into 2 into 1, which comes out to be 720. So why this factorial operator? Why am I telling you about it? Because this will be frequently used not only in this lecture but in other relevant probability problems as well. Okay. So let's start some simple examples. for understanding how we can count different ways, number of ways an experiment could be performed. Let's have an example from biology. The simplest protein molecule in biology is called vasopressin, and it is composed of 8 amino acids, right? And those amino acids are bonded together in a particular order. So order is quite important in this example. That is, to have a particular form of vasopressin, it is necessary that a particular order of these amino acids should be there. Okay, so if these 8 amino acids were placed in a hat and drawn out randomly one by one, how many different arrangements of these 8 amino acids are possible? That is, actually we're just saying that if we were to draw the amino acids randomly one by one, in how many ways can we do it? You see, actually when we are drawing things one by one, we can consider it that we have 8 slots, because there are total 8 amino acids. So there are 8 slots, and we wish to see in how many ways can these slots be filled. So for the first slot, you can see if these letters represent different amino acids. So for the first slot, I can choose from any of these 8 amino acids. So for the first slot, I have 8 choices. And now for the next slot, since repetition is not allowed, for the second slot I am left with 7 choices, right? For the next one I am left with 6, and so on. So there are 8 factorial ways in which this selection could be performed. And this is the reason I introduced the concept of factorial, because it's going to be too frequently used in this lecture. Okay, next let's have another concept, permutation and combination. So permutation is an arrangement of n things arrangement of r things taken out of n things, and order matters. As you proceed through the upcoming slides, you will understand better with the help of examples. For now, let's focus on one thing, that if we have to choose r elements out of n elements and order matters, then it's a problem relevant to permutation. Whereas if order does not matter, then it's a problem of combination. I will talk about this one, and the one which is shown here in the bottom. I will talk about this formula later on. For now, what you have to keep in mind, that if you have to arrange r things out of n things and the order matters, then the problem at hand is relevant to permutation. And if the order doesn't matter, then the problem at hand is relevant to combinations. Okay, so suppose we have let's say these 4 objects: table, paper, book, and marker, and we have to select 3 at a time. You see, what I can do in the first slot, one hypothetical selection would be that a table is chosen, and the second, a paper is chosen, and the third, a book is chosen, and so on. There are different ways in which the 3 things could be chosen, right? So if I have to find out that in how many ways could this be chosen, and here I'm assuming that the order matters, whether a table is chosen first, followed by a paper, and then a book. Suppose that you have to put them somewhere in a place, so you need to know what is being there in the first slot, and what's there in the second, and what's there in the third, so that you can physically place them, maybe in a classroom. So if you have to place the table first, then let's say a carton of paper, and then a carton of books. For now I'm assuming one carton is one entity, that's why it's written just book. So if order matters, and I have to count that in how many ways can I select 3 things out of these 4 things, so it will be equal to 4p3. So 4p3 means 4 factorial divided by 4 minus 3 factorial. Coming back, You see, permutation of n r. In the above example, the n is 4 whereas r is 3. So 4 factorial divided by 4 minus 3 factorial, which comes out to be 24. So you can count that these are 24 different ways in which I can select 3 things out of these 4 things, and my assumption is that order matters. Okay, another example of permutation. Suppose you have downloaded 12 songs on your computer and you want to put 4 of them on a CD. And then in how many different ways can you do this? You see, if you are making a CD, let's say to play or to enjoy while you are driving, and CD or USB, even CD is quite less used nowadays, so maybe we can replace CD by a USB. So whatever, a CD or a USB, you have 12 songs in it and you want to see in how many different ways can you do this. So basically you have 12 songs, right? And you want to copy 4 of them in your USB. So there are 12 different songs whereas you are choosing 4. So 12p4 is the 11,880 different ways and you can choose these 4 songs. So this was the second example for permutation. Next, let's say a permutation lock will open. You know that there are keypad locks or the numeric lock, and the order matters. For example, if the lock passcode is 0123, then you have to follow this particular order to unlock. So a permutation lock will open when the right choice of 3 numbers from 1 to 30 inclusive is selected. How many different lock permutations are possible? You see, there are 1 to 30. There are total 30 numbers. Had this been from 0 to 30, we would have of course considered that as 31, but now we have 1 to 30, so 30 numbers, and we have to choose 3, so 30p3 will be this number, 24,360 different ways that the passcode for this permutation lock could be set in. And this is the reason that permutation locks are so difficult to hack or to guess their keys. Okay, so further to clarify what is the difference between combination and permutation, because when I introduced the concept of permutation and combination, what I told you that in permutation order matters, whereas in combination order doesn't matter. But sometimes students find it difficult to understand when to apply permutation and when to apply combination. So let me further elaborate onto it. So a combination is a grouping of outcomes in which the order does not matter. The formula is NCR, which is n factorial over r factorial into n minus r factorial. So one example, how many pairs can be made from a group of 6 people? Total we have 6 people or 6 persons, and we want to see how many pairs could be made. So you see, if 2 people are chosen, for example, if we write it Jin and Tom, or we write it Tom and Jin, these are basically same pairs, because no matter it's written as Jin and Tom or Tom and Jin, these are necessarily the same pair actually. So we are going to apply the formula of combination 6C2, which will give us 15 different ways. Now if we analyze the same example but in a different scenario, there are 6 people in a contest. In how many ways can first and second places be awarded? You see, now order matters, because whosoever is chosen in first place will be you can say given the first prize, whereas whosoever is chosen in the second draw or second combination, that person will be given second prize. So Jin first and Tom second is different than Tom first and Jin second, and therefore the order matters, and we will apply the permutation formula. So this is how you can have a mental picture of when to apply permutation and when to apply combination. Okay, so to further differentiate the two, permutation is the number of ways to arrange things, A combination is again the number of ways to choose things. So generally in permutation we are interested in how to arrange, for example the permutation key lock example, whereas in combination we are generally interested in choosing things, for example making a pair rather than arranging a pair, like in this example, in how many ways a pair could be made. So we were interested in making a pair. Then in permutation order matters, in combination order doesn't matter. Generally permutations are for list arrangement, whereas combinations are for groups or for pairs arrangement, right? Okay, so now if we have different type of scenarios, as we said that if order matter and repetition is allowed, then the possibilities are n raised to the power r. Remember that the formula NPR is assuming that the repetitions are not allowed. But if order matters and repetition are also allowed, then you will not apply the formula of NPR, you will rather apply the formula of n raised to power r, right? If order matters but repetition is allowed. If order matters but repetition is not allowed, then we will apply permutation formula NPR. Now coming to combination, if order doesn't matter, then it's you could say domain of combinations. If repetitions are allowed, we will apply this formula NCR expansion, n factorial over r factorial divided by n minus r factorial. If repetition is not allowed and still order doesn't matter, then we are going to apply this formula, right? Okay, so proceeding further, suppose you want to analyze in how many different ways can a card registration number having 4 digits be issued. We are assuming that the card registration number consists only of 4 digits. So we know that there are total 10 digits, 0, 1, 2, so on till 9. And we know that repetition is possible. For example, a card registration number could be 01112. And order matters because a registration number of 1122 is different from registration number 2211. So it means that repetition is possible and order matters. So which formula we will be applying? See, order matters, repetition allowed. So we will use this formula n raised to the power r, which means 10 raised to the power 4, which is 10,000 different ways the card registration number could be issued. Next we have the example order matters and repetition is allowed. Pardon for this spelling mistake, this is not repletion, this is repetition. So order matters and repetition is allowed. Suppose you want to analyze in how many ways can a card registration number having 4 digits be issued, and a digit can only be used once, right? Now we are assuming that the repetition is not allowed. So there are total 10 digits, repetition is not possible, and order matters, as we said that 1, 2, 3, 4 is different from 4, 1, 2, 3. So total ways are, if I go back to that slide, which case it is? Order matters, repetition allowed. Going back, order matters, repetition allowed. So I am going to use this formula, n factorial over n minus r factorial, which is the permutation formula. So 10 factorial because 10 digits divided by 10 minus 4. So we comes, the answer is 5040 different ways the card registration number could be issued. Okay, another example, a store has 6 different fitness magazines, 3 different news magazines, right? 6 fitness magazines, all of these are different, and 3 different news magazines. If a customer buys 3 magazines at random, find the probability that the customer will pick 2 fitness magazines and 1 news magazine, right? Actually, we want to see in how many ways can we choose 2 fitness magazine and 1 news magazine, right? And of course over here order doesn't matter, right? The customer is not interested whether he got a particular fitness magazine in first place or in second. So there are 6C2 or 15 ways to select 2 fitness magazine from 6 fitness magazine, right? How many magazine total fitness? Six fitness magazines were there, and you wanted to choose 2 fitness magazine. So in total there are 6C2 different ways in which you can choose the fitness magazine. And by the way, this calculation is not shown here, that I will just explain. If we were to choose 1 news magazine, so how many total news magazines are there? 3, and we have to choose 1. So how many ways will be possible? 3C1, right? So if we were to calculate the overall total possible ways, we will multiply 6C2 by 3C1, and that's how, with a little bit of further calculation, it's very easy to calculate the end or the required probability. Now consider a problem that will further differentiate or illustrate the difference between combination and permutation. Consider the set PEN. How many 2-letter words, including all nonsense words, that is whether they have a meaning or not, they are all included. So this is the set PEN, and we want to see how many 2-letter words can be formed. So if I enlist the 2-letter word, and they will be P with the E, then P with an N, then E with an N, E with a P, and so on. So we will have 6 different possibilities, right? Now consider the set consisting of 3 males, Paul, Ed, and Nick. For simplicity, let's write P, E, and N, except for Paul, Ed, and Nick. And how many 2-man crews can be selected from this set? Now you see that the answer will be PE, that is Paul and Ed, Paul and Nick, or Ed and Nick, and that is all. We are not going to include EP again. You see, PE is done, so EP will be same, because that would mean again selection of 2 same persons. So that's how you can see that over here in the second scenario you are actually discounting. Why you are discounting? Because order doesn't matter here. So it's a domain of combination. In the above example where we had words, order mattered. That's why we considered PE different from EP, because that was just a selection of words from this, whereas this was selection of a, you could say, pair from 3 persons. So this is a typical example of an application of combination. Okay, so what was the difference? Although I have already explained, but let me further strengthen your concept by just reading what's written here. Both problems involve counting the number of arrangements of the set P, E, and N, taken 2 at a time, right? In both problems we had the same set P, E, and N, because even in the second problem I shortened the Paul's name by using the letter P, Ed by E, and Nick by N. So in both scenarios we had the same set P, E, and N. However, in the first problem the order of the arrangement mattered, since PE and EP were considered 2 different words, and they are 2 different words, right? PE is P and EP is maybe EP. So these are different words. Whereas in the second problem the order did not matter, since PE and EP represented the same 2-man crew. PE means implied Paul and Ed, and EP implied Ed and Paul, so necessarily the same pair. So we counted this only once. So the first example was concerned with counting the number of permutation of 3 objects taken 2 at a time. The second example was concerned with the number of combinations of 3 objects taken 2 at a time. So I hope that this settles, or this makes it clear the difference between permutation and combinations. I will do some other examples, further examples, to further strengthen your concepts. In how many ways can you choose 5 out of 10 friends to invite to a dinner party? Consider that you want to arrange a dinner party and you have to choose 5 friends out of those 10 friends.
So just imagine, does order matters here? Of course not, because even if you invite the friends in order A, B, C, D and E, or A, C, B, D and E, these are necessarily same friends. I mean, so that means that the order does not matter here, and we are going to apply the formula of combinations, which is 10C5, and we know that 10C5 is equivalent to 10P5 divided by 5 factorial. Even if you don't write it this way, directly calculate 10C5, which is 10 factorial divided by 5 factorial into 10 minus 5 factorial, and you'll get the answer that you can invite 5 friends out of 10 total friends in 252 different ways. Okay. 6 friends want to play enough games of chess to be sure that everyone plays everyone else, right? There are total 6 friends, and they are interested to play as many games of chess as possible in a manner that each friend plays against the everyone else, against each of the remaining friends. So how many games will they have to play? You see, there are 6 players and we have to choose 2 at a time. So how many total possible ways? Once again, order doesn't matter, because friend 1 versus friend 2 is considered same as friend 2 versus friend 1. So we apply the formula of combination 6C2, which comes out to be 15. So they'll need to play 15 games to ensure that each player has played against the remaining other players. Okay, next example. In a lottery, each ticket has 5 one-digit numbers 0 to 9 on it, right? Each ticket has 5 one-digit number 0 to 9 on it. You win if your ticket has a digit in any order. What are your chances of winning? So you see, it's very obvious from the question statement that the order doesn't matter here. So there are total how many digits? 0 to 9 makes it 10 digits, and you have to select 5. So 10C5 is 252. So there are 252 different ways that you can win this lottery. In scenario B, you would win only if your ticket has the digits in the required order. What are your chances of winning? Now, order matters, so you will apply the formula of permutation, that is 10P5, and you can easily calculate that it will come out to be 30,240 different ways. So your chances of winning are 1 out of these possible ways, whereas in scenario A, your chances of winning were 1 out of the total possible ways, which is 252. So you can see that in scenario B, your chances of winning are lesser as compared to scenario A, because in scenario B, not only you need to have the winning numbers, but you also need to have them in the required order. Okay, next problem. In how many different how many total arrangements of the letters in Mississippi are there? You see, this is a 11 letter word, and we have like 11 slots. So if I say that the first slot, if I have to choose any letter from this word, I have 11 options for the first slot, 10 for the second, and so on. So it comes out to be 11 factorial, or this many different ways. But now let's see how we can further refine this scenario. What happens if I switch the third and fourth letter in Mississippi? You see, the third and the fourth letter, they are same. So if I switch the third and the fourth letter in this word Mississippi, these permutation wouldn't be considered different, because the third and fourth both are S. So the third and fourth letter are both S, so switching them changes nothing. So that means that the calculation we just did, that is 11 factorial, it is not respecting the fact that there are some repeated letters in this word. So how we need to adjust for these repeated letters or repeated arrangements. So how to do that? You see, this is an 11 letter word in which I is repeated. You can see 1, 2, 3, 4. So I is repeated 4 times, S is repeated 4 times and P is repeated 2 times. So I am going to deflate the total 11 factorial by these repetitions, 2 factorial, 4 factorial and 4 factorial. So these are 34,650 different ways in which we can arrange the letter out of the word original word Mississippi. Let's impose a further restriction on it. How many arrangements are possible such that the two P's are separated, that is, they are not appearing in consecutive slots? So the problem is that we don't want P's to be adjacent or appearing together. Suppose I remove P and calculate the permutation. So if I remove P, the word becomes this, right? So this is just one arrangement of that word. So I have to see in how many different ways. So there are how many? These are total 9. So because we have discounted P's, so 9 factorial divided by, once again, how many repetitions? I can see that 4 repetitions of S and 4 repetition of I. So total 9 divided by 9 factorial divided by 4 factorial, 4 factorial. So 630 different permutations are there if we altogether delete the letters P. But we don't have to actually delete. We have to see where those P's could be placed. So suppose before and after each word or each letter, in fact, I keep an empty slot. Actually, I am trying to see that where the P's which we deleted earlier, where they could be fitted. So if one P is here, the other should be here or in the other slot. So if I count, there are 10 different blanks. So we have 10 blanks and we can choose any 2 blanks to insert P's, because in these blanks the P's will not be adjacent. So we need to calculate 10 and we have to choose P. So we have 10 blanks and we have to put 2 P's in this. So 10C2 is 45, right? Because order doesn't matter. Once again, whether the first P is here or the second is here, that doesn't matter. So 10C2 is 45. So there are 45 different ways in which I can insert P's in these 10 blanks. So in how many total ways can I do the actual arrangement where P's were not to be adjacent is 630 multiplied by 45. Recall that we got 630 total permutation multiplied by 45, because both of these conditions should be met. So these are necessary conditions, therefore we are multiplying and we get that there are 28,350 different ways in which we can rearrange the letter Mississippi such that the P's are not adjacent. Next, I introduce the concept of arranging things in a circular pattern. Suppose we have these 2, 4, 6 and 8 different balls, and each of them has a different unique color, and I have to arrange them in different circles. Suppose if I put the gray ball here followed by the orange and so on. If I see this arrangement, is this arrangement different from these 3? Apparently it seems that this is different, but if you have a closer look, even here gray followed by orange and blue and so on, this is again gray followed by orange and blue and so on. So these are necessarily you can say same actually rotations of this given arrangement. So if we have n balls, here we have like 8 balls, so in general if we have n objects or n balls, we are going to take the factorial and then deflate by n. Why n? That the actual n objects could be arranged or rotated in n different ways, and these are n different, apparently different but actually same. So we deflate the actual factorial by n. Had this been arranged, for example, if this were to be arranged in straight line, then we would have said n factorial. But now we are arranging in circles, so I will say n factorial divided by n, because as we just saw that there are n different rotations for the same thing. So n factorial divided by n comes out to be n minus 1 factorial. So this means that whenever we have to arrange things in a circular manner, then we are going to say that the answer will be n minus 1 factorial. So number of circular arrangements of n different things is n minus 1 factorial. But if the number of circular arrangement of n different things when clockwise and anti-clockwise arrangements are not different, that is, no matter a particular sequence is followed from clockwise rotation or anti-clockwise, we are going to further deflate the n minus 1 factorial by 2, because then the possibilities will be further reduced, because clockwise and anti-clockwise will be considered same. Now if you have let's say total n objects and you have to choose r of those, right, and you have to arrange them in a circle. So number of circular permutation of n different things chosen r at a time when clockwise and anti-clockwise orders are taken as different, then it is given by npr divided by r. And if the clockwise and anti-clockwise are not different, then we'll further going to deflate it by 2, just like we did here in part B. So this will be npr over 2r. So this is how you can calculate different number of ways in which different random experiments could be performed. So I hope that this lecture was clear. I will post my email address in the comment section, and you can always reach me out once you drop me an email. If you want to get professionally connected, I will share other modes of communication as well, such as social media or my phone number as well, if you wish so. So thank you for watching the video with patience, and I hope that you will subscribe to the channel and you'll watch the other videos in different playlists. By the way, this channel Rao Hub, I do explore all the playlists. It has many playlists such as on statistics, on econometrics, on probability theory, on human mind, positivity, and even a playlist on comedy genre as well. So I can ensure that this is sort of a multi-dimensional display of, or you could say multi-dimensional portfolio of the knowledge that I have, and I would love to share it with you. So thank you for watching, and hope to see you again soon.